Lesson 9-2, quadratic functions. Our goal today is to be able to graph quadratic functions of the form ax squared plus bx plus c. Here's an example of an applet that demonstrates quadratic functions. So right now our a coefficient is 1.79, our b is 1, and our c is 3.2. So notice our vertex is up at 3.2. So that vertex either goes up when our c value is positive, or it goes down when that c value is negative. The a value tells us how wide or narrow our graph is. So notice as our number gets bigger, that graph gets narrow. As that number gets smaller, closer to 1, it gets really wide. And then if that a value is negative, it opens down. So wide and narrow, up and down is for our a value. So those are some things we'll talk about in this lesson. So our essential understanding is that in a function that's quadratic, the b value affects the position of the axis of symmetry. So again, with that demonstration, if I get my parabola set nicely here, that b value tells us where that axis of symmetry is going to be. So it just kind of slides around from left to right. So what we're going to do on this example down here, it says, sketch the parabola. Label its vertex and axis of symmetry. Notice the axis of symmetry is the same as the x value of the vertex. So our formula today is negative b over 2a. And I do like to sneak that negative right into that b value like this, so I don't have to worry about it. So negative b over 2a. So we're going to define what a, b, and c is, first of all. So looking at our function, our a value is 1, our b value is negative 4, and our c value is 7. So we plug into that negative b over 2a, so we get positive 4 over 2 times 1, which is 2. Then if we plug 2 into our function, 2 squared minus 4 times 2 plus 7, out would come 3. So that's the other half of our vertex. So if we plot those points, this is where our vertex would be. Because that a value is positive, I know it would open up. So I'm just going to sketch this one. Something like this. And then our axis of symmetry, using this formula down here, I get x equals 2. So again, it's going to be a vertical line that hits our vertex at positive 2. So here's where the x-axis lies, and it hits when it's at 2. Let's try another one. Graph this quadratic function. So let's first find the coordinates of the vertex. So looking at our function, we need to define what a, b, and c are. So a is 1, b is negative 6, and c is 4. Then we will plug in our formula, negative b over 2a. So we get 6 over 2 times 1. That simplifies to 3. So that's the first part of our vertex. That's the x value. So in terms of our table, we want to put 3 in the middle of our table. So then we can find 4 and 5. And then above the 3, we get the 2 and the 1. So what we're going to do is we're going to take that 3 and plug it into our function. So what I could do is plug it into my graphing calculator, and because this 3 is positive, I don't have to use parentheses. So I get 3 squared minus 6 times 3 plus 4, and it spits out a negative 5. So that's the other half of our vertex. Then we have to find out what goes along with 4 and 5, and then remember that that rainbow effect is going to happen with our parabola. So I plugged those numbers into the graphing calculator, and I decided to plug in the 1 and the 2. So 1 squared minus 6 times 1 plus 4 gave me negative 1. And 2 squared minus 6 times 2 plus 4 gives me negative 4. So in my parabola, I can fill out the rest of my table using that rainbow. So if I plot my points, I'll do my vertex first, and then I'll plot 4, -4, and 5, -1. There's the first half of my parabola. And this dotted line provides where my axis of symmetry is going to be. So this is the front half, now we need to find the back half. So I went forward 1, up 1, so now I'm going to go backwards 1, up 1. And then to place the other one, I'm just going to line up here. See how I'm 2 spaces away from my dotted line. So I'm going to go 2 spaces away from that axis of symmetry as well. And then I'm going to go ahead and add my curve to demonstrate my full parabola. So again, here are the steps. First, find your vertex. And remember, you're using the formula -b over 2a. Once you find that, then you're going to go 2 below your parabola and 2 points in front of your vertex, And then number 3, after making the table, you're going to draw in half of your graph, think about your axis of symmetry, and then do the second half of your parabola. So let's try that again. Looking at our parabola, we want to first define what A, B, and C are. -2, -8, and -3. Our goal is to find our vertex. So our formula is -b over 2a. So let's plug in the value. We get a -2. So there is the first half of our vertex. So we could go over here and start filling out our table. We know -2 is our vertex, so it's going to go in the middle of the table. Then we add -1 and 0, and then in front of -2 would be -3 and -4. So you can choose to use the graphing calculator or your regular calculator to figure out what the other half of the answer is for the vertex. So here's what it's going to look like on my calculator. -2, and then in parentheses, -2 quantity squared, -8, parentheses, -2 minus 3. So the answer to that is 5. Then what I'll do in my graphing calculator is I'm going to plug in for -1 and I'll plug in for 0. So notice the -1 happened here and here, and I got out a 3. And I plugged in a 0. I wouldn't have to use parentheses, and that gives me -3. Then I remember that that rainbow effect happened because of that axis of symmetry. And now I'm going to plot my points. So here's my first half of the graph using my vertex. And then remember that axis of symmetry is going to go through that vertex. So I'm just going to sketch that in with that dotted line. And then I'm going to go ahead and reflect over that the rest of my graph. So I'm 1 away, so I'm going to go 1 away. And then down here, I'm 2 away, so I'm just going to stay on that same line and go 2 away. And then again, I'm going to add my curve to demonstrate that my parabola goes on and on forever down on both sides of my vertex. So why don't you pause the video, try this one on your own, and see if you did it correctly. So the first thing you should be doing is figuring out what A, B, and C are. Use your formula to figure out the first half of your vertex. That first half of that vertex will tell you where to start in the middle of your table. So 2, after 2 comes 3 and 4, before 2 is 1 and 0. So we need to figure out the rest of that table. So here's what that would look like on that graphing calculator. Because we're plugging in a +2, we don't have to use parentheses. So there's a negative in front. So -2 squared plus 4 times 2 minus 2 gives us a 2. Plugging in a 3, -3 squared plus 4 times 3 minus 2 gives us a 1. And then if I plug in 4, I have -4 squared plus 4 times 4 minus 2, which gives me a -2. And then again, I reflect those points up to the top because of that axis of symmetry. Final step would be to plot those points, keeping in mind that the axis of symmetry would happen right there. The last thing we'll talk about today is a vertical motion model. This equation models anything that has a projectile motion. Here's an example. Throwing a shot put has a projectile motion because it travels in a parabolic path. Another example would be throwing a ball or the path of the water at a fountain. So in our model, we have these variables, h, which is the height of the object, t is the time the object is in the air, and v is your initial velocity. So that's going to depend on your scenario. And then c is your initial height, which is also going to depend on your scenario. So we're going to be plugging in values for v and for c, depending on what our problem says. So here's our first example. Drew Brees throws a football to one of his many talented receivers. The football has an initial upward velocity of 40. So that was our velocity that goes right in for v. Then we have Drew releasing the ball at exactly 6 feet. So that's the distance from here to here as where his arm is. So that number would be plugged in right here. The ball is caught in the outstretched hands of a receiver 4 feet above the ground. So that's kind of happening at the end, so we don't worry about that number. So if we had to write out a model, we would get y equals negative 16t squared plus 40t plus 6. So we just replaced the v and the c with the numbers that were given to us. So now we're going to answer some questions about this example. What is the maximum height of the ball? Well, a max height is the same thing as a vertex. And we have a formula for this, which is negative b over 2a. So in this example, our b value is 40, and our a value is negative 16. So if we plug that in, we get 1.25. But remember, that's a number that goes into the function. So that is a t, which stands for time. So that's seconds. So that is actually answering this question. How long will it take to reach that max height? So this answer is 1.25 seconds. So we have to figure out the other half of our vertex. So we're going to plug that number in. So if you plug that number in on your calculator, it gets pretty long, and the outcome is 31. And that would be how high it is. So graphically, here's what we're talking about. The ball started at 6 feet. It got up to its max height, which is its vertex, after 1.25 seconds. And it hit 31 feet. The next question asks, how long did it take the ball to reach Marquise Colston, the receiver catching the pass? So I think we can kind of guess at this. If it took 1.25 seconds to get to its max height, to get to our catcher's, our receiver's arms, I think it would double that length because of that symmetry. So if from here to here is 1.25, if we double to get there, we're looking at about 2.5 seconds, and we're just estimating. Question number 4, what is a reasonable range for this function based on the graph? So remember, range are possible y values. So looking at our graph, this is our y-axis. So it's looking like y values have to happen at 31 feet or below. And could a height ever be negative? No. So we want to be greater than or equal to 0, and also less than or equal to 31 seconds.